CENTRIC, the EU project on real-time neural receivers for pilotless communications. So this is essentially 3 years of work. So I will introduce what is a neural receiver, and then we will look into how we can extend that concept towards pilotless communications, which is clearly a topic for maybe for 6G. So first of all, what is a neural receiver? So we focus now on the uplink shared channel in our 5G system. So the receiver sits in the base station in the G node B essentially. We look into a multi-user MIMO setup where multiple users want to communicate information from one point to the base station essentially. And what is typically done is, right, you have a couple of these signal processing blocks in the physical layer like modulation, pilots, and OFDM, and so on. And then at the receiver side, we typically have the kind of inverse operations that reconstruct the transmitted information bits, and then we measure the performance metric like the bit error rate or block error rate. Now, the idea of a neural receiver is to replace particularly the channel estimator, the equalizer, and the demapper by a single neural network that learns to reconstruct or to estimate the transmitted information bits from the incoming IQ samples, essentially. You can have different variations of these receivers. You can include the block decoders at LBC decoder. You can exclude it. You can include the channel estimator and so on. But that's the version that we have here in our setup. And then for the channel, it can be either a simulated channel, a 3GPP channel model, or it can be a ray trace channel model, or it can be also a hardware channel. It can be a real hardware in the loop test bed. And we will hear more about that later in Keysight's talk, where we have actually also taken this concept and put it onto their hardware test bed essentially. Now, one additional word about the setup. So all this is done with our Shona link level simulator. This is all open source, so you can essentially run that even in your browser, so you can reproduce all of the results that I'm presenting. Everything is publicly available and actually also for free. That's a nice thing with the resource. Now let me kind of look at this problem from two different perspectives now. So this problem of reconstructing or transmitting information bits, or this neural receiver problem essentially. So we can look at it from the 5G perspective and from the machine learning perspective. So from 5G, we are focused on the 5G push, so the uplink shared channel. That means essentially the inference of the machine learning perspective happens at the base station, where you may have a bit more compute than on the UE side. We have a multi-user MIMO configuration. In this case, we consider 2 streams. Could be also 4. So in the paper we have, I think 4 is maximum we show. We have 4 receive antennas in the system, and we have assume we have a 16 QAM, but it could be also a QPSK or 64 QAM. In total, we are simulating 100 megahertz of bandwidth, so 273 PRBs for the 5G experts here at 30 kilohertz carrier spacing. Now, from a machine learning perspective, that essentially means that we have an sensor that has a shape, and can assume that batch size is 1, at least during inference. So we have 1 received slot. We have a couple of subcarriers. In this case, it's 3,200 subcarriers. It's 12 times the number of PRBs. We have a number of OFDM symbols. So we process entire slots essentially. So 14 OFDM symbols in this configuration. And we have the 4 receive antennas, and then we treat complex valued IQ samples as a real imaginary part. So we have actually 8 2 times 4 values at the last dimension. And now this tensor is actually kind of processed by the neural network, and at the output we get the recovered information bits. Now that are quite a lot of bits actually. When you look at such a standard 5G slot here, we have like 170,000 codeword bits per stream. We have 2 streams, so in total we have 340,000 bits. And now from a machine learning perspective, we are doing essentially 340,000 parallel classification tasks. So you can think of it like cats versus dogs, but just 340,000 times during one inference. And then after channel decoding, assuming a certain code rate, it's like almost 100,000 bits for one inference of the neural receiver that is actually reconstructed. The training is now just done similar to standard classification tasks, use binary cross entropy loss, and we average that over all codeword bits and all streams and so on. You can also average over the decoder, different decoder iterations and so on. Yeah, so that's kind of the setup that we are working on. And I mean, this is really an overview talk, just 20 minutes, so keep it high level. Now, there are a couple of issues when you design such a network. First of all, you need to have a real-time inference capabilities. That's something I will focus on in the next slides. But you also need to focus on a couple of other things. And here's a prototype network that we have developed within the CENTRIC project. So first of all, you need to support essentially a flexible number of users. So in multi-user MIMO, you can schedule more or less users. This is really a dynamic setup and it's changing all the time. So what we have is actually an architecture where we can add more or less users and then can kind of change without retraining the architecture of the network. We call it a graph neural network inspired architecture, where we define essentially how many users we have. We have then an iterative type of network that essentially defines the depth of the network. So we can add more or less layers that allows us to control the complexity. We'll see that also later, which is very important because depending on your hardware platform and compute capabilities, you can then kind of match the number of iterations such that you can run it in real time, whatever is your real time constraint on your platform. We have everything in either as CNNs or point-wise MLPs. So that means essentially we can dynamically change the number of PRBs, the number of subcarriers essentially, which makes it also more flexible because that's something that dynamically changes in 5G systems. Typically, the number of used subcarriers is constantly changing and you cannot retrain a network whenever these parameters change. Right, and then don't want to go into the details of the network. We have kind of open sourced it, but it's really it's quite a complicated stack of layers essentially. There's just one thing I would like to point out here is that we have now the MCS scheme, so the modulation coding scheme. So essentially, the modulation order is changing also constantly. The code rate is less. The LPC code rate is less of an issue. So the code rate part of the MCS scheme is actually agnostic to the neural receiver because we have still the classical transfer block decoder. That's what I've shown on the first figure. But for the modulation scheme, we need to be able to configure that also on the fly. And actually, I can hear someone who's not muted. I can hear some noise. Yeah. Anyway. So for the modulation scheme, what we do is we train different input layers, so input layers essentially for different MCS schemes, and then we can dynamically reallocate them or replace them. So when for one user, when the modulation scheme changes, then we replace essentially the input layer, but we keep the rest. So 90% of the weights can be kept actually constant. That's the idea of this adaptive modulation encoding scheme. But the main focus of this talk is actually on real-time inference of such a receiver architecture. So what we have done within CENTRIC is we have kind of optimized this architecture now, and I would like to kind of summarize a bit how you can do that. So first of all, we have done training using our Shona link level simulator. For those of you who are not aware of it, it's actually an open source project. You can use it for rapid prototyping of communication systems, link level simulations, and now also system level aspects. And it's written in TensorFlow. So the networks are actually described in TensorFlow, and then you can just export them to any inference engine or inference library that you want to use for deployment, essentially. In this case, we are using TensorRT as real-time inference. There is a bit of glue code required or compatibility code for making it 5G compliant. So the architecture that I've just described is actually this inner part of the receiver. And again, there are many aspects here hidden in this network. But there are a few points I would like to highlight what you need to make this 5G compatible. And one aspect where we were struggling for a while with 5G is that the DMS, so the pilots in these slots that are transmitted, they are rotating essentially on a per slot basis. So they are changing all the time. So you cannot train a neural receiver or neural network to overfit to a specific pilot constellation because it's changing anyhow. And in a multi-user setup, it's even more complicated because it depends also on how the multi-user system is actually configured. So what we do is we do a so-called least square channel estimation and feed that as additional input to the neural receiver. So least square channel estimation is like the simplest channel estimate you can do, and this gives us an initial guess essentially for the neural receiver. Feed that as second input. in that sense, strictly speaking, we are not totally replacing the channel estimator anymore, but we need this this initial estimate essentially mostly because we don't know how the pilots are rotated essentially. And then at the output, we extend the receiver also by not just providing the estimates on the bit, so LLRs, but also providing channel estimates. And that helps to kind of improve the convergence during the training. So we train actually on a multi-loss or dual loss essentially, where we train on the estimated bits, but also on the channel estimates. And it also helps to push the training quite. Now, after training, we can export that to ONNX as an example. So standard open neural network format, import it in TensorRT. This is the inference library, and run essentially latency measurements of our architecture, and then we can actually see is it real time or not, and then we may need to do some adjustments in the architecture. We need to identify the bottlenecks and so on. That was actually a pretty hard task. It took quite a while to do that, because you also need to keep an eye on the block array performance of your system. You cannot just remove layers. If the performance of the receiver degrades, then of course this doesn't make sense. So people sometimes say machine learning is more art science, so you really need to tweak that manually and identify the bottlenecks of your architecture. But one thing that really helped was actually by making the depth of the network adaptive. And you can do that by stacking same blocks together in a kind of iterative fashion, similar to you do multiple LDPC decoding iterations. We have now different iterations in the network. So we run the same blocks or the same building blocks essentially of the network multiple times. We define it as an iteration, and then we can control the depth of the network actually by changing these number of iterations. And we have now an architecture. We do 2 iterations. We call that real time, because you'll see that in a second that runs quite fast. And then we have one neural network that we call a large network. It has up to 8 iterations, and then we can compare the impact on the block error rates and so on. All right. So when all this started, we were at like 20-25 milliseconds inference latency for one slot, and for the experts in 5G, that's actually far too much. So real-time budget is between, I don't know, 500 microseconds to a millisecond. Depends a bit on the system configuration. So we targeted a millisecond was our optimization target. But there are also a couple of things. It was just TensorFlow, no TensorRT. We didn't really optimize for no batching. That's something we learned during the project, that when you do real-time inference, you cannot do any batching because you cannot queue multiple slots that would already add up latency. So you need to do the processing on a per sample basis, essentially. And also quantization is, of course, a topic. So that was all done float 32. So after all these optimization steps, we kind of matched the millisecond inference latency target, kind of went down to float 16 quantization, and also reduced the number of weights. So the final architecture has only like 140,000 weights, which is can be, in terms of number of weights, it's a super small network, but also inference requirements of a millisecond are quite tough. Let's have a look at the block error rate performance. This is the transport block error rate, so really on a transport block level. The latency of the real-time architecture is now just below the millisecond, what was the target, running on an NVIDIA A100 GPU. And then the large network is just a baseline essentially of how good it can be. We could add more latency essentially, and that's around 3 milliseconds latency. So yeah, the performance now, yellow is actually just a standard least square estimator, LMS-ED mapper, and then the real-time node receiver gives us quite a performance boost. This is more than a dB, where we have as a reference K-best kind of genie-aided, or not genie-aided, but kind of an optimal receiver essentially, but super complex. So that's also in practice hard to implement essentially. And then the large node receiver is actually close to this kind of optimal baseline for this system. And then there's the gray curve. This is now the genie-aided curve here, where we assume we have perfect CSI, so there is no channel estimation. We assume we perfectly know the channel essentially, just to get a lower bound of how good we could possibly be. And that's quite impressive. So essentially we get the almost perfect performance at a lower complexity compared to this purple curve here. But still, there's something when you look at the kind of the inference latency for different number of iterations now. So the larger one is the one here at 3.1 milliseconds, while the real-time version is the one at 0.96 milliseconds. We can actually also measure now as a required SNR at a specific target block error rate. This was 10%. And we can see that if we put a threshold here, so a real-time threshold, then there's a performance degradation just from the limited compute capabilities. And that makes perfectly sense. So we can really, the conclusion of this experiment is really that we need to do these comparisons between different architectures and different receivers and so on under some realistic real-time constraints, essentially. Otherwise, the comparison is not fair. We know how we can make it better, but we don't know how to make it faster. That's essentially the challenge here. Okay, so nonetheless, the result is still quite good, and it's a very strong performance here. And that's for a very large number of subcarriers. When we make the number of subcarriers smaller, then the compute latency also reduces, then we get also better performance. So it really strongly depends on the system configuration. Now let's go to the second topic here. Yeah, not too much time, so let's look into end-to-end learning. Now we extend this concept. We have now the no receiver. We go back to single user setup, so we have now just one user. And now we sort of adding, or it's actually a concept of adding now also trainable components to the transmitter. And in this case, we add a trainable modulation scheme. So instead of having the standard QAM modulation, we now have a trainable constellation scheme here, and we remove the DMS pilots. So DMS pilots means essentially in 5G we have these pilots, and they are kind of they cost, of course, transmission rate, because you cannot transmit data on these DMS resource elements we send the pilots. And the idea is now that the network learns. So we use now gradient descent. So we jointly optimize the two networks here, the constellation and the node receiver together without the DMS. And then we want to ideally learn somehow to communicate and learn how to compensate, communicate without the need for any pilots. So we have a higher data rate, essentially. That's the promise here. So just a bit of a background. And so in 5G, we have these slot configurations mentioned already, and there are pilots at specific positions. So this is one example configuration. So blue, so this is a number of FDM symbols, so 14 per transmitted per slot. And then we have here 12 subcarriers. This is a toy example. Typically, we have more. And each blue field is a data symbol, a QAM symbol, while the green symbol is actually a pilot. So this is a known position, a QPSK pilot is typically, and then there's some mask position for multi-user MIMO. And then we have the standard 16 QAM, you know that from just standard communications lecture. But now in the idea of end-to-end learning, we totally remove these pilots. So we have more data symbols, essentially higher data rates. And what comes out of the training is actually a new constellation. So this is a non standard QAM, essentially. So it's not a rectangular QAM anymore. So it's clearly geometric shaping that comes out of the training here. And there's an interesting observation that there's the one, let's say, anchor point, essentially. So can interpret it intuitively as a superimposed pilot. That just comes out of the gradient-based training. So we just use the same training as we use for the node receiver, essentially. Okay, so let's do a quick intuitive interpretation what is actually happening. So when we look at the new constellation that we are using, so we just, similar to classical QAM with gray labeling, we just map the bits to symbols and then we transmit these non-uniform constellations here. When we look at what is actually transmitted at the transmit power in a transmitted slot, this is just one example that we have actually picked here, then you can see these yellow points with very high power. This is actually whenever this anchor point, so it happens randomly, right? So when we send random data streams, and just from time to time we send with probably one out of 16, we send this data symbol. So you see these yellow points here, and they act as anchor point here. That's kind of the interpretation. Now at the receiver side, we can also look at the channel estimation error. This is actually, when we use this constellation, it works super well. The constellation, the channel estimation error is relatively constant. But when we do now an experiment, and we just do that just to understand what is happening, we kind of reverse engineer what happens. So we now remove this one anchor position by modifying the data stream. So we just modify the transmitted bits such that the symbol never occurs. So essentially, we just never send this stream of 111 anymore. And then what we have actually is we have a significantly worse channel estimation. So just going back here, we are at, I don't know, -25 to -35 regime, while then we are at the -10 dB actually. So the channel estimation totally breaks down. And we can now repeat this experiment for all other symbols here. Did that. So x-axis now is the symbol index, which symbol we removed from the data stream. And y-axis is actually the channel estimation error. And we see that only for this one symbol, this effect happens. So only when we remove this anchor symbol, essentially, then everything starts to break down. And that's intuitively underlines or proves, it's not a mathematical proof, but it kind of shows that this is really used as an anchor for channel estimation, has a special meaning for the channel estimation. All right, now let's come to an end and let's summarize. We'll actually skip this or just quickly go over the slide. So when you measure this now, it's very complicated to compare the two systems because you have a system with pilots and a system without pilots, so a standard system with pilots and a new system where we don't have the pilots, so we have different data rates. And kind of comparing the two systems is actually not that easy. That's why we use the so-called good put, and that's not that common. That's why I would quickly introduce it. So the idea is that the good put is essentially how many bits you can successfully communicate in a given amount of time or using a different amount, a given amount of resource elements, essentially. So you need to kind of take into account the block error rate of the system, or bit error rate, and the number of resource elements that were actually occupied. That's kind of it's similar to the spectral efficiency, essentially. Now, when you look at this, we have had a hardware in the loop demonstrator of this. So we can then measure the block error rate of a standard neural receiver. That's the green curve, the one that I have shown before, and of the actually that was wrong. The green curve is actually the Pilotless scheme, right? So it is actually close to this what we had before was kind of the maximum likelihood approximation. And we see we are super close. So we are not outperforming the baseline, but we are very close. And that's exactly the effect. We are now communicating at a higher data rate. So we have the same block error rate, but communicating at a higher data rate that doesn't show up in the block error rate. And that's why we use the good put as a metric. And we can actually see that the good put, so the amount of information we communicate in a given available number of resource elements, is actually a bit higher. And that's kind of the increase in data rate, essentially. And the blue dots here, these are measurement points that we got from our test bed. So we kind of really had a test bed showing that you can run this setup, and they match pretty well to what we had simulated before. So the curves are simulated, and the blue dots, they are measured. They are pretty good pretty accurate on the line. So this is always good if your test bed gives the same result, confirms the same results. So with that, I'm at the end of the talk. I would just like to make one small announcement. So we have just released an extension of Shona, so this open source project that I was talking about. It's called the Shona Research Kit, and we now also support, let's say, real-time experiments. And we are having one tutorial where we are showing essentially how it's using open interface. So it's real 5G stack. And we have now also integrated this node receiver there, and we run this as an over-the-air demo. So this is not just something that exists on slides and simulations. So we can now really connect a commercial modem to this neural receiver and run it in real time, running on the NVIDIA Jetson platform, essentially. Just as a kind of another proof of concept that you can really run these neural receivers in a real system, essentially. With that, I'm at the end of my talk. Just let me quickly summarize what we have achieved in the CENTRIC project, and just a very big picture overview. We have the real-time efficiency or real-time constraints. So we really optimized receiver architecture. That always looks simple, but was a lot of work. We have dynamic reconfiguration, so dynamic MCS schemes, dynamic number of users, and so on. And we have looked into these pilotless schemes, so what I have shown in the second part of the talk. It's all online available, all papers, all code, everything is publicly available.